Hey everyone. So the screen is black. This is my first slide, and I have to apologize because I was just in Bangalore. I got here this morning from Bangalore, and I had a little bit of trouble doing that. So they repossessed my plane. Which, I mean, not my plane, obviously. Like, obviously, they repossessed it. But the plane that I was going to be on, got repossessed, which is not a thing that I knew could happen. Like, a plane repo man came and jimmied the plane lock and flew the plane away, I suppose. And I didn't know that was a thing, but it's a thing. If you get too behind on your plane rent, they take your plane away. And no money, no plane, no flight. And that was a journey. KLM was sort of helpful, but mostly not. And then I had to fly to Mumbai and then to London, and I'm sitting on the plane being like, when is Brexit happening? Am I going to land and we will already have Brexited and it'll be like 1984? And that didn't happen. So long story short, there's no slide. And so if you don't mind, I'm just gonna like draw it right now. So. Looks nice, right? Yeah. And we'll do this. Yeah, that looks cool. And one of these. Boom, there. You can read it, right? That makes sense to you? I mean, okay, you might have to interpret it a little bit because I also didn't have time to actually like render the stroke data, so I guess I'll tell you how to interpret it and then you can interpret it. So so each of those points is a input event, and the color of the point is the data from the input event. So the red component is the X, and the green component, the blue component is the Y, and then green is the pressure. So now you can sort of read it. No. Okay, it's still hard. Yeah, it's still hard. So how about we do this maybe? We'll render the force differently. We will make the size of the dots, we'll make that proportionate to the force. And it's not really helpful, is it? I mean, it's cool, it's not really helpful. Okay, so we'll do another thing, which is, I have a color picker on here that you cannot see, haha. And we'll render the colors correctly. And no, we won't. Oh, yes, we will, there we go. Okay, and that's actually even less helpful, it occurs to me, because now you have no way of knowing the positions at all. Maybe say, I'll have it move the points to where they would be on the screen. We'll kind of do this coordinate system transform between the iPad and the screen. And, there we go. I have a title card. Everyone loves title cards, right? So that is, drat. That is my name. I'm Ashi Krishnan. I'm Rakshesha on Twitter, and that is the repo where you cannot go because I forgot to open it before this talk, but you will be able to, like, in 1 minute after I get off stage. Sorry about that. Okay, so what I was just having you do was be a vertex shader, basically. So what's a vertex shader? A vertex shader is, well, the thing that I was trying to make you be. Or, better, less circular answer. In OpenGL, a vertex shader is a program that runs on every single point and determines how that point, that vertex, is going to be transformed and presented. So basically, where will it be and what data should be associated with it. So our vertex shader looks like this. This is a fairly small one, but let's talk about some terms. So uniforms, like you see on the first line, those are inputs to the shader that are uniform across all the vertexes. They don't change. And so the one uniform we are accepting in this shader is the perspective transform, which is 16 numbers, or is the projection rather, which is 16 numbers that describes how to turn points on the stage into points on the screen. And then we have attributes. Attributes are also inputs, but they are different for each vertex. And so we've got 3 columns, 3 buffers of data representing our stroke. We've got position, force, and color. And then finally, we have some outputs. So we've got a couple of built-in outputs. We have GL position, which is where should this dot be. And we have GL point size, which they both do pretty much what you would expect. And then we have this one custom output, this varying variable called vColor. And it's called varying because it varies. Not just from vertex to vertex, but from pixel to pixel. And speaking of pixels, we get to also write a program that will color each and every single pixel. And that's this. This one is not really doing very much. This is just taking the color from the Vertex shader and telling OpenGL, hey, you should use this for the color of the pixel. So that's it. It's like pretty straightforward. So how do we go from this to me doodling on here and having it get drawn up there? So the answer is through what is probably the most over-engineered system that I've ever built for a talk. We listen to stylus data on the iPad, and we spray these events across a WebSocket to a server running on my laptop. The server is, of course, running inside of Parcel, because why the hell not? And there's like a lot more layers in there. I can't even tell you. There's a structure library, like a struct library in JS, which lets you describe interleaved data formats, because for some reason I was like, gosh, it would just be too much overhead to send a JSON header. And the server writes things to column IO files, and then there's like a messaging protocol that's peer-to-peer, and it was ridiculous. But anyway, here's how we get the stroke data and then draw it. So we have these vertex array buffer cells. We point them at files on my disk, is essentially what a data node is. And we start to get events whenever they update. So I can still draw on this, and it'll just like update live. And then those get read directly into buffers on the video card. And when I say directly, I mean through many, 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 many layers of kernel drivers and whatnot. And we render them like so. So we have this vertex array object, and we call set attributes on it, and we say, here are some buffers that you should use to feed data into the Vertex shader. And then we draw the whole thing. I have too many screens, really. Problem here. Yeah, so this like whole with parameters thing says like, okay, with blending on and with this blend function, which is the blend function to use, please draw the program. So we're using a library called LumaGL, which is this really, really wonderful WebGL library made by the Uber Data Viz team. It's a great library, sort of ethically questionable company. And there's also all this other sort of garbage around here, which is the reactive library that it's sort of an experiment in making a evil clone of React that we're going to talk about later, but not too much in depth because I like you. Okay, so when we put it all together, we get what my friend calls light bright mode, which, let me tell you, is already pretty satisfying, at least when I don't have to reload it, which does happen somewhat often on this freaky Wi-Fi connection. Sorry about that. All right. Great. Nope. So I can kind of like make little doodles, and because it's pressure sensitive, a lot of this is like actually the joy of having an Apple Pencil. This device is really, really nice and really good at like giving you a feel for that you're actually working with some actual medium. Still, we've got this kind of like retro 8-bit aesthetic thing going on. And one thing that we could do to make it feel a little bit more naturalistic is maybe make it not so sharp. So if we could have the opacity of these pixels depend on the pressure that I'm using, then it would be better. And that's a fairly straightforward transform in the fragment shader. So now all of my strokes are pressure dependent in both their size and in their opacity. And this now kind of, well, it kind of looks like a crayon almost. We've gotten up to crayon level, I would say. The code for that is not so different from the code we saw before, except we've added this component where we multiply the alpha by the force down on the last line. So that's nice, that's kind of cool, but some limitations. One thing you might notice is that we don't have like a very large number of colors. Like we've got this sort of aggressive fuchsia, and we have brilliant teal, and on the whole, it's sort of a debug CGA aesthetic. And the only reason for that is I didn't add more buttons for more colors. But there's other ways to get colors, like this. So these are colors that are coming, as you can maybe suspect, from an underlying image, which makes it really easy to draw cool things, right? Because there's a picture right under it. You can't see the picture, but I can see the picture. And it's a nice experience, but I really feel like it would be better if this were somehow, if it were more shaded, if it like felt more natural. Oh, by the way, you might be at this point being like, Ashi, is there any React in this talk? And that's a really good question. And to that I want to say watercolors. I think watercolors would really capture the light falling from the sky on this city. And fortunately we can do that. Kind of. I mean, it's a watercolor. Is it a watercolor? Is it a crystal that's being grown? It's sort of unclear. But whatever it is, it's pretty cool, and it does feel pretty nice to work with because the strokes sort of keep doing a thing after I'm done stroking them. Whenever I tap an area, it sort of like fills out and bleeds, not exactly like watercolors would, but in a similar way. The way we're doing this is all in the fragment shader. I hit that key expecting that it would do something, which of course it will not. And this fragment shader is a lot more involved than the previous one. Basically, we're doing a flood fill of sorts. A flood fill or a graph traversal or computing a Voronoi diagram. So we run this program for every single pixel. And for every single pixel, we look at its neighbors and we're like, hey, are any of you closer to a seed, to an actual data point? And if you are, I'm going to take your color. The way we store distance to an actual data point is in the alpha component. So we just say, we won't use alpha for alpha blending. We'll use alpha to store distance and just use RGB colors. And that works pretty well. There's some behaviors in the shader that I don't totally understand. Like it has a pretty clear southeast bias. Like if I just draw a line and it's filling, it wants to fill southeast. And I don't know why that is. Someone who knows more about shaders might know why that is. I should also maybe tell you that I don't know what I'm doing. I can sort of like figure this out, but if you really ask me like, gosh, what are the vagaries of numeric precision or what, yeah, I don't know. But this looks cool, doesn't it? Yeah. I should have mentioned that at the start, and maybe when I was submitting the CFP for this talk, things might have gone very differently. So we've got a bleeding fragment shader, and with that we can do some pretty neat stuff. Like, here's a pretty good one. So this is actually 3 photos that I've taken, and I've sort of stitched them together myself by picking which of the photos I'm using as the sampling basis, and just kind of going to town and letting the fact that they're all being bled together on the same watercolor layer kind of do the right thing for me. And this is actually 3 photos of one Philippine island called Batanes, which is a really lovely place that I would recommend you visit very respectfully. It's very special. You have to be a member of the indigenous people of the Philippines to even own land there, and they seem to be like developing it in a very conscious way. So beautiful place, highly recommended. Good place to go and meditate on shaders. So we've seen the shader code driving this, which is basically the brain behind the whole thing. But like your parents and like a number of world leaders, there's a lot that I am not telling you. And there's a whole bunch of machinery back here that's setting up the graphics context and the buffers and updating what needs to be updated over there and up here, and just syncing the two. But not redoing everything on every frame, because that would actually get a little bit too slow, especially if I keep putting down points, which I'm definitely doing. So this would be a great moment to say, and it's all in React, but it's not. In some sense it is. So the root of it is in React. This is the entry point, and look, there's a react.dom.render call, and that's kind of the end of the very familiar things, I think, because it's rendering the player, which is the presentation player, and it's rendering this loop component, which has got to be very suspicious, raises some more questions than answers. So React is responsible for managing these state transitions between slides, between scenes. But then for managing the WebGL objects within a scene, I didn't use React, mainly because every time I've tried to use React for something like this, I started to regret it immediately before the presentation. And it turns out that I kind of regret doing this immediately before the presentation, so maybe I just regret giving talks right before I give them. But React doesn't seem, this is I'm nervous to say this in front of this audience, because someone will tell me how I'm wrong. I am not smart enough to make React programs that reconcile once every frame and are performant. Every time I do that, I find myself like watching my Chrome tab just shudder to a halt. Eventually, like at first, I'll do something like this. I'll be like, I want to animate a component, so I'm going to write like the canonical form as an animator, which attaches to an animation callback, or to a frame request, and sets state, and then renders its children with that dependent on the current timestamp. That is like what an animation is. And then I have like enough of these in a page, or I have a big lump of virtual DOM under one of these, and it doesn't love me anymore. And so that's one reason. There's another actually better reason for having a slightly different approach for managing the WebGL object, which is that React really, really wants data to flow one way. This is actually exactly what Peggy was talking about. You have like this high degree of predictability where like data comes in and it goes through a deterministic map, and then it goes to the page, and that's like everything. But that's not what we're doing here. We actually want the opposite of that. We want this like messy set of interconnections where the output of this shader is fed back into itself in order for it to continuously like process this sort of chaotic visual. And so for that, we're using a spreadsheet. Kind of. We're kind of using a spreadsheet. So this is the spreadsheet. This is not exactly a spreadsheet, but it kind of follows the same idea, where each of those little blocks is a cell. And cells can hold values, or they can hold expressions, they can hold functions, they can have evaluators in this parlance attached to them. And there are references between them. So an evaluator can reference other cells by their pattern, and that creates links between them. And whenever one cell changes, the system knows, oh, I should go and recall all of these other cells. And it doesn't matter if there are cycles. It doesn't matter if mainly cycles are fine, because we throttle cells to being evaluated once every frame. And if there's a cycle, you'll just continuously evaluate those two cells forever and ever and ever, and that's fine. It's also easier in this system to create references between different cells. And so let's look at that. So here's the evaluator that's running right now to make this effect. We've got some boilerplate at the top. Evaluators can be called as though they are, they take props, as usual, and a cell, which is the place where they will store their data. And if you don't give them a cell, they return a pattern, which is the equivalent of a virtual DOM node, like a virtual element. And so they're kind of isomorphic in that sense. So that first line is boilerplate to make that possible. And then everything else is kind of like this weird alternate universe React, where this $ function goes and looks up a cell by its pattern, creating it if necessary, and creating a link between this cell and that one. And then whenever any cell that I depend on updates, I'm going to get called again. And so these evaluators get called again and again in order to update the state, and they can both make changes to the cell's value, and they can also decide that they want to listen to new cells. They can create new edges in much the way that you can, in much the way that you can't go and just create new hooks. The way React hooks work is that they're dependent on being called by order. The way this works is that every single hook is keyed, which means that you don't have to specify all of them all at once. And our diffing system becomes sort of much more straightforward because we can just detach all of the edges from a cell, run its evaluator, and see what it attaches to. And any cells left orphaned after we go through a whole pass, we just kill. So this is a weird experiment, and it has some benefits. Namely, I can talk about things like the recording of a stroke or a texture with a particular image in it, and be guaranteed that there's only one such cell in the entire system. If I create a texture for a particular image, that resource is bound to the cell and it will never get duplicated. I'm not going to have 20 copies of it, which is great for some things and then terrible for some other things, because maybe I do want 20 copies of it. If it's a mutable object, then if I'm scribbling into a frame buffer, I don't necessarily want that frame buffer to be shared. And so that's what this $child thing does, is it disambiguates that. Lessons from this: I wish that I had done some of this, that I had glued some of this into React more than it is. This is glued into React. You can put an evaluator inside of a component, and it just works. That's why there's the loop context being provided. But it's not as tight a binding as I think would be good. So version 2, we're going to try and leverage React strengths, which are having a good sense of structure reconciliation with the strengths of the system, which are having a good sense of resource sharing. All right. Oh, let's look at some pretty pictures. So we can do kind of a lot with just the kind of basic pattern of writing a fragment shader that looks at all of the neighbors of each pixel and just ruminates on that. We keep processing the output. So this one is a blur, which quickly, as you can see, turns into darkness. The blur code is fairly straightforward. We're just averaging all of our neighbors. A similar effect is something like this after image. It looks similar, but then it's like a little bit more persistent. And it looks to me like what happens if you stare into a bright light and then you close your eyes. Like you can still see this ghostly effect. And I think it reminds us of that ghostly effect because this is basically what is happening in our neurons when we stare at a bright light and then we close our eyes. The code for that is we do one more neighbor visit than just doing a blur. So we go and find we call it the mass, the sum of the weights of all of our neighbors, and then we do a weighted average of all of them rather than just an average of all of them. And that sort of makes us take on the value of our brightest neighbor, which is why we still retain an image after a long time. This is my favorite one of the simple shaders. It starts out like you would expect, and then it quickly becomes kind of cinematic. This reminds me of what happens when the point of view character is dying, but they're not actually dying. They're going to wake up in the hospital. But the colors along the edge are really beautiful. The code for this is exactly the same as after image, only we added this factor, this 1.002, where we're just slightly brightening everything, every color that we take on, and that leads us to just brighten the entire image until we converge to whiteness. It's really a fascinating look at how just tiny tweaks iterated over and over and over again will produce really dramatic shifts in behavior. All of these shaders have converged. So the blur tends to converge to black or gray. This will converge to white basically always. What I would really love to see is a shader that continues to evolve but then doesn't converge. And to approach that, I decided to just take something that I knew evolved and often didn't converge, namely a cellular automata, namely the game of life. So this is the game of life running in a fragment shader and driven by stylus input, which is pretty cool. This is pretty satisfying, I've got to tell you. It feels like I'm playing with a little bit of, with these little ants. It's a little small, right? It's like these tiny grains of sand that are nevertheless creating stereotypical structures. You can see gliders, and you can see blinkers, and all these things. I think it might be a little bit more dramatic if it was bigger. Oh yeah, here's the code. The code is, same kind of thing you might use to write Game of Life in any other scenario. You look at your neighbors, you count how many of them are alive. We're counting aliveness based on how bright the cell is, and then we never darken a cell entirely, we just dim it so that it's too dead, and that lets us retain the colors. So we could make life lower resolution, and then this is it's sort of more clearly 8-bit, more clearly a chunky life. Probably too chunky. I think I want something a little bit less. Yeah, this is sort of a nice size. This looks like a video game, but none of these really feel like something more than the game of life. What I think I would really like is all of them stacked together. I want a high resolution one and a low resolution one, and that'll give us this visual sense of depth. Like that. This, I think, is the most fun when used with the rainbow effect. Yeah, this I gotta say is super satisfying. This is the kind of thing I was going for. I feel like I am drawing an intergalactic civilization. Or if I choose the black marker, I feel like I'm destroying an intergalactic civilization. Oh, no, it's a black hole. Oh, I should, there's our rainbow black hole. So this is kind of messy, and it's not entirely predictable, and that's really kind of all the charm of it. We spend so much time working on reliability and determinism and repeatability, and React is all about those things, right? Data goes in, DOM nodes come out, never a miscommunication. And a lot of things should be that way. Like if you're working on flight control systems, definitely that you should aim for that. If you're working on self-driving cars, please, for the love of God, don't do anything like this. Except we are doing that. This is the whole thing with machine learning, is it's a whole stack of linear algebra that we're not really sure how it works. But nevertheless, like repeatability is often good, but we're not like that at all. Right? We are reliable because we are messy. We are interesting because we intersect with ourselves and because we are these recursive processes that you can't really predict, because we just keep evolving and ruminating and like processing our own output, and before you know it, we will have become something very different from what we once were. So this is a brush in just a different kind of art palette, like something from the cracks between coding and painting and meditation. And there's a whole world in here that I am really excited to explore, like this world of chaotic non-determinism, where paintings paint themselves, where every drop of ink is a seed, and where everything comes alive. Thank you.